Alright guys, so today we're going to talk about electron orbitals and how they came about and what they are. So we've kind of heard about electron orbitals, but let's go for a brief history lesson. I'm not real fond of history, but sometimes it's necessary. So models of the atom. So the atom is it's bound under what's called atomic theory. And if you remember back to the scientific method, a theory is our idea of the truth, but it can be changed as our understanding changes. So the atomic theory has changed over time. So Dalton gets credit with the first atomic theory. And he thought that atoms were tiny indestructible spheres. So here's his model. So essentially he thought that all things were made of atoms, right? But atoms were kind of like marbles, right? You just put a whole bunch of different marbles together and they're solid. Indestructible means they're just solid. You can't destroy them. You can't make them. That's our conservation of matter. Almost 100 years goes by, and technology increases, right? And we get a guy named Thomson. Now, I spelt this wrong, so if you do a crossword puzzle later, take out the P. So Thomson, right, comes out with the plum pie model, or the plum pudding model. So Thomson did some investigations with a thing called a CRT, or a cathode ray tube. And what a cathode ray tube does is it shoots an electron beam. So the old computer monitors, the big boxy ones, or the old big giant TVs that were real thick, right? They were cathode ray tubes, and they bent electron streams to make pixels or pictures in little small dots on your screen. So Thomson, almost at 1900, started playing around with a cathode ray tube, and he found that anytime he brought a positive side of a magnet, right, to the tube, the electrons bent up toward the positive. And if you brought a negative plate to it, right, the negative plate down here, the electrons bent away from it, right? So he said that the movable part, right, so Thomson's contribution, he said the movable part of an atom, right, was like electricity, had a negative charge, right? So his model was kind of like if you cut a watermelon in half, right? The plum pudding model is that the electrons were stuck in the positive goo, and they were negative, but you could remove them, right? So he discovered electrons, and then shortly after, things will start to pick up speed here, Rutherford, really important scientist, right? So you'll notice with Thomson's model, there is no nucleus, right? So Rutherford started playing around with radioactivity. And radioactive decay is where pieces emit from an atom, right? The atom starts to come apart spontaneously. So he took an alpha ray emitter. So an alpha particle, we're going to learn later, is a helium core, right? So essentially what it is, it's a helium core without electrons, right? So it's a helium core without electrons. So it's a really small solid piece. And he develops an alpha generator, and he shoots it at gold foil. Now gold foil, if you've ever done crafts or ceramics, it's a super thin layer of gold, and you can paint it on things with a paintbrush. It's really thin, right? It's as close to as an atom thick as you can get. So he shot this alpha beam at gold foil, and he has a detector around, right, to detect where electrons will go. What he finds is almost all of these go straight through, right, and then other ones deflect at various angles, right? So almost all of it goes straight through, and some of it deflects. So Rutherford discovers the nucleus, right? And he said there must be some solid nucleus, right? And the nucleus is very, very small, but most of the atom must be empty space, right? So he comes up with a new model of the atom, right? So he comes up with what's called the planetary model. And if you think about how planets work, right? The sun would be like the center of the atom here, right? And all the electrons are like the planets, and they all orbit around nucleus at the same distance. Right? That's his model. It's his planetary model. Now, he has a student right? A student named Niels Bohr. Niels Bohr becomes very important. And you're probably most familiar with the Bohr model, right? So Niels Bohr, you can see, is just a couple years after Rutherford, and he's Rutherford's student. And he doesn't necessarily, he likes all the stuff that he and Rutherford did, but he doesn't necessarily think it's correct. So Niels Bohr comes out with this quantized model, right? So Niels Bohr kind of makes a modification of the model, and this is the one that you probably learned in school, right? So in the center, if I take sodium, so if I take sodium, right, sodium in the middle has positive, it has protons and neutrons, right? So we'll say that it has 11, we'll say that it has 11 protons in the center of the atom. So what Bohr said that around this, are quantum energy levels. And if you look at your periodic table, right, those periods represent different quantum energy levels. So the first level is n equals 1, second is n equals 2, and then I have n equals 3, because sodium's on the third level. And then he says, in the first level, I have 2 electrons. And they're orbiting around the nucleus like it was the sun. In the second level, right, I have 8 electrons, right? And in the third level, I have 1 electron, right? And if I add them up, I get 2 and 8 and 1, that's 11, right? And that's the atomic number of sodium, right? But these all, he says, they all orbit around in fixed orbitals, right? So those are called quantum energy levels, quantum orbitals. Now, if you look at the periodic table, the reason why he chose those, if you look at n equals 1, you count across, there's a maximum of 2 electrons. If you look at n equals 2, there's 1, 2, 3, 4, 5, 6, 7, 8. That's why there's 8. And n equals 3, right? Sodium's in that first position, and that's why there's 1 up there, right? So he comes up with this model. And the reason why he comes up with this model is he says that energies can be quantized. So let me kind of explain this. So quantum lost my pen. I'll say it represents So quantum energy level represents the maximum distance an electron can be found from the nucleus. All right, so these electrons here at n equals 1, the reason why they're at that distance is that's how much energy they have, and that's the maximum distance they can be found. An electron orbital then electron orbital is an area where an electron is likely to be found, right? So Bohr thought they were fixed, right? So I'm likely to find these 2 electrons in this distance from the nucleus, right? But he said that energies or electrons can be quantized, right? So these first 2 electrons, if you look here at this model I drew, these first 2 electrons have 1 quantum of energy. These next 8 electrons in sodium have 8 quantums of energy. And this last electron has 1 quantum of energy. But what he says is if I give some energy to that last electron, I can make that electron jump to n equals 4. Right? So if I give it a quantum of energy, I can get it to jump to n equals 4. Right? But the problem is that leaves what's called an electron hole here. Right? So it's an unstable configuration. So I can give it energy, but that electron will jump back. When it does, it will release a photon. Right? And a photon is a packet of light energy. Right? So it'll release a photon, and the packet of light energy will have exactly the amount of energy that it used to create that jump. Right? So essentially that's what it talks about here, right? So an electron is quantized, it jumps to the next energy level, right? From 3 to 4 is what I showed you. Right? When an electron jumps, it's considered to be in its excited state. Right? When it falls back to what's called its ground state, right, it releases a photon. And that photon is a packet of light energy. And it says all that in this picture here. Right? And those electrons jumping is essentially how we get light. Right? When you turn electricity on, it heats up something in that light bulb, right? And it causes electrons to start jumping back and forth. And as it does, it creates all this light. That's how the sun, which has a hydrogen and helium core, produces that yellowish light that it produces. Okay, so the problem with this is there's a guy named Heisenberg who was about the same time as Bohr. Right, and he started looking for electrons in orbitals. Right, he couldn't find them. Right, so he came up with his uncertainty principle. Right, so where Bohr thought the atoms were, or the electrons were on fixed orbitals or fixed distances, Heisenberg showed that they weren't. Right, so Heisenberg's uncertainty principle, he says that it's impossible to know where an electron is at one particular point. You can only be sure where it's not, right? So where it wasn't on orbitals. So that led the way for 1926. Remember, Bohr was 1913, I believe. 1913. So in 1926, a guy named Erwin Schrodinger comes up with a model that we kind of use right now. It's called the quantum mechanical model. So now, we're going to say that electrons, so the way this changes, so instead of electrons being on orbitals, they represent what are called cloud densities. Right? And cloud densities say that an electron the electron now travels from the nucleus to the border. So the electron is always moving in the nucleus, right? But the limit of how far it can travel away from the nucleus is defined by its quantum energy level. And he said, to his calculations, right, these cloud densities are more dense toward the nucleus than toward the edges of the quantum energy levels. So he said it's more likely that an electron is to be found near the nucleus than far away from it. Okay? So Schrodinger came up with this quantum mechanical model. Now, if you look at his orbitals there, and his orbitals have different shapes and different paths. Another problem with Bohr's model, right, it was one-dimensional. And we're not one-dimensional, we're three-dimensional. So Schrodinger is going to come up with this probabilities in orbitals to occupy all space in 3 dimensions. Okay, so we'll transition from what we've done to probabilities in orbitals. So Schrodinger stated that orbitals can be more correctly referred to as electron clouds, right? An orbital being the region around an electron. So we say that each orbital can hold a max of 2 electrons, each with opposite spin, right? So there are 4 different types of orbitals, right? We're going to go over them, S, P's, D's, and F's. But each orbital can hold 2 electrons, right? They come in pairs, right? Electrons come in pairs. So they can hold a max of 2 orbitals, and each has a different spin, and those different spins cancel out the electrical field they create, because a spinning electron creates a force in one direction. So if I have opposite spinning, they cancel each other out and make it neutral. If you have a magnet has aligned electrical orbitals making a positive and negative side, right? If you took Earth science, you probably figured that out. And that's why the Earth has a magnetic pole, by the way, because it all spins in one direction and it creates a magnetic pole. Okay, so Schrodinger's orbitals. So there's S, P's, D's, and F. So orbitals right, affectionately known as stupid people don't fly. That's how I remembered it in college, right? So the s orbitals, so if you look at your periodic table, right, we'll go more off my pictures now then. All right, so the s orbitals are spherical in shape, right? The s orbital begins at n equals 1. So it's the only orbital at n equals 1, right? So my s orbitals are here, and you could actually imagine helium being right there. Now helium's put over at the noble gases because it shares properties, but there are only 2 atoms, right? And s equals 1, right? So this is quantum energy level 1, so this would be 1s, right? And 1s can hold a maximum of 2. So there's only one 1s orbital, okay? So let's continue to go through. So the p orbitals, right? So the p orbitals is dumbbell shaped, right? So if you lifted weights or anything, they mean by dumbbell shaped is like the dumbbells you lift when you lift weights, right? So it's kind of pinched in the middle. So if you look at our picture up at the top, right, this is my S, and these are my P's. Now the P's, if you think about, so this would be the P in the X direction, this would be the P in the Y direction, and if you can imagine the 3rd dimension coming in and out of the board, this would be the z-axis, right? The 3rd dimension coming in and out of the board, right? So the px, the py, and the pz. So there's 3 dimensions for p's, right? So there's 3 different orbitals. So the p orbital system begins at n equals 2, right? So this is my p here. Remember, I have n equals 1, n equals 2, right? So it begins in the 2nd energy level, it's dumbbell shape, begins in the 2nd. There are 3 orbitals in the p system, right? It has different axes, like I just told you. So it can hold a maximum of 6 electrons. Because I get 2 electrons here, I get 2 electrons here, and I get 2 electrons here. So it can hold a maximum of 6, and if you count the width across the P, right, that block right there, right, there's 6 atoms in there. Right? Each atom represents an additional electron. You got the d orbital systems, right? The d orbitals are dumbbells and donuts. So you can see they're all dumbbells, and there's one donut right here in the second picture there. Right? It begins in the 3rd energy level. Right? So I get n equals 1, n equals 2, n equals 3, and these are my transition metals here. Right? Now, the D is what's called a suborbital system. So, but this is 3p here. Right? So it's a suborbital system, so it's a subbonding orbital system. We'll talk about that in the next lecture that I'm going to do. But the transition metals start at 3d. Right? Right? So there are 5 orbital systems. Remember, each orbital can hold 2 electrons. So, you can see that they're the dxz, so they go in the kind of the planes in between the y, the x, and the z coming in and out. So they kind of go in the in-betweens, right? They can hold a maximum of 10 electrons, right? So 5 has 2 each. So 2 electrons in here, 2 electrons in here. Alright, so each of those can hold 2 electrons, 2, 4, 6, 8, 10, so 10 electrons maximum. Alright, it's considered a suborbital to the 4s. So after 4s, then we get our 3d. And in the next lecture, we'll go into that more and more and more. But those are our transition metals. And then we get our f orbitals. Right, so our f orbitals are down here in the rare earth elements. Right, so it begins in the 4th energy level. So this is a subsystem. Right, there are 7 orbitals. Right, so if there's 7 orbitals, there are 14 electrons. So if you look at, there's a pattern to the periodic table. There's 1s, right? So it goes by odds. 1s, 3p's, 5d's, 7f's. You get 2 electrons, 10 electrons, right? Or 2, 6, 10, and 14. All right. I considered a suborbital to the d block. So the d is already a subsystem, so it's a sub-subsystem, right? Okay. So, if you think about it, here's kind of a summary for you, right? So if you take a picture of this page, it'll give you some things. So the N1, right, sublevel 1s has 2 electrons. N equals 2 has 2 sublevels, 2s, 2p, right, has 8 electrons. The 3 has 3 sublevels, right, 3s, 3p, 3d. There's 18 electrons total because you have 3 electron systems, and n equals 4 has 4 electron systems, or a max of 32 electrons. Right? And we'll talk about that next time. There's another way to look at it. If you look at your periodic table, right? This block over to the right, which you drew when you did your periodic table, right? That's your S block, right? Outline over here, starting from boron to neon. Right, we're going to exclude hydrogen because hydrogen is part of the S. Right, that's your P block. Right, and then I have my D block and my F block. Right, so S, P, D, and F. Stupid people don't fly. Stupid people don't fly. Right, because they don't have that money to buy plane tickets. All right. So anyway, that was it for today. Not for today, but for this lecture, and I'll talk to you soon.